Welcome back. Problem 3-15. This problem is taken from chapter number 3, Mechanical Properties of Material, and book name is Mechanics of Material by R.C. Hibbeler. So statement of problem is the rigid pipe is supported by pin at A and 836 guy wire BD. If wire has diameter of 0.25 inch, determine the load P if end C is displaced 0.15 inch downward. So you can see this is the pipe having a point load at point C, and there is a wire A36 which is BD, and that is supporting it, and at point A there is a pin support. So due to this load point P, this point C will move downward at a distance of 0.15 inch. So you have to determine this load. So I have written the given data. The rigid pipe clear diameter of wire BD is 0.25 inch, and from mechanical properties table you can take the value of E modulus of elasticity of A36 wire, and its yield stress is 36 KSI. So let's start with the solution. So first step is that you can see that this wire will apply a load in this direction, which is represented as FBD. So if you take this rigid pipe BAC and draw the free body diagram, it will be like this. Clear? This is point A, where when you remove this pin support, you will be having a reaction force in horizontal direction as well as vertical force in upward direction. This is point C, where we have a point load P, and this is point D, where we have to show the effect of this wire BD on this pipe, and let this force is FBD. Now you can see that FBD is making an angle theta with horizontal. So let this is the angle theta. Clear? So we know that sine theta will be equal to 4 perpendicular over base, which is perpendicular over hypotenuse, which is 5, because BD is hypotenuse, and it by using Pythagoras theorem you can calculate this, and this will be equal to 5 feet, which in turn is equal to 60 inch. Clear? And we know that cos theta will be equal to 3 over 5. Now what we will do is that we will find this force BD by using equation of equilibrium. So first equation of equilibrium, or equation of equilibrium that we will apply, is sum of all moment about point A is equal to 0, taking the counterclockwise movement as positive. So this FBD will have two components. One is horizontal component, this will be equal to FBD X component, and the second one will be the vertical component, and that will be equal to FBD Y. Clear? Since at point A this force AY and AX and AY are passing through, they are not producing any movement, so only force which is producing movements are P, and perpendicular distance is given as 6 feet. So you can see this is 6 feet, and this is producing clockwise movement, so it will be negative. So I will write minus P times 6. Now the second force that is producing movement is the vertical component, and perpendicular distance will be 3 feet. So you can see this is 3 feet. And what will be the perpendicular vertical component? This will be equal to FBD Y component into perpendicular distance is 3. Their sum must be equal to 0. This component, horizontal component, is not producing movement because it is passing through point A. So what we will do is that we will find this minus 6 times P. Now we know that horizontal component FBDY will be equal to FBD sine theta. How? If you take sine theta, so sine theta will be equal to this FBDY divided by FBD. So FBDY will be equal to FBD sine theta. And we know that sine theta is equal to 4 by 5. So I can write FBD into 4 divided by 5 multiply by 3 is equal to 0. So from here, when you solve this, you will get this FBD will be equal to 2.50 times P. So this is our first equation. This is equation number 1. Now it is given that due to this load at point P, clear, these C points will move downward at a distance of 0.15 inch. Clear? So this pipe will move like this. It will be like this, which will cause this point D to move this to new point D dash, and there will be stretch in this wire BD, and this will become like this. Clear? So what we are going to do is we will find this D dash, which is not known. So again, what if I draw a right angle triangle over here? You can see like this one. So by using similar triangle, if I take this larger triangle, this is the larger triangle. If I take this distance divided by this 6 feet, let me write it, 0.15 divided by 6 feet, that will be equal to this DD dash divided by 3. So from here you will get this DD dash will be equal to 3 times 0.15 divided by 6, which is equal to 0.075 inch. Now we know that this length BD is equal to 5 feet, that is equal to 60 inch. Clear? And we know that D dash. So if you look at this triangle, this is the triangle. Clear? So what we are going to do, we will find this BD dash. So how we will find this? So if I draw it a triangle like this, this is B point, this is your D point, this is your D dash point. Clear? And this is your B dash D dash. Clear? So this distance was 0.15 0.075 inch. This is 60 inch. So what is this angle? So again you can see this is 9. This is, if you take sine of theta, clear, that is 4 divided by 5. So theta will be equal to sine inverse 4 divided by 5, which is equal to 53.13. Clear? So total this angle will be equal to 90. This is alpha. So alpha is equal to 90 plus theta, and that will be equal to 143.13 degree. So by using this triangle, we will find this length of BD dash. So length of BD dash will be equal to, we will apply this formula, BD square plus D dash, DD dash square minus 2 into BD multiplied by D dash into cos of angle between them, which is alpha. So you can see this length, square of this length plus square of this length, and the cos of minus 2 times length of BD into DD dash into cos of angle between them, which is equal to alpha, and that is 143.13. And when you take the square root, this is cosine law of triangle. So when you put the value, length of BD dash will be equal to 60 square plus 0.075 square minus 2 times 60 into 0.075 into cos of 143.13. So when you solve this, you will get length of BD dash or stretch wire will become equal to 60.060017 inch. Now this is the change in length. This is the new length. So what we will do is that the normal strain in A36 wire will be equal to, we know that strain is in wire BD is equal to change in length divided by original length. So change in length, new length is length of BD dash minus original length is LBD divided by LBD is original length. So just put the value 60.060017 is new value minus 60 is original value divided by 60. So it will give you strain in A36 wire, which is equal to 1.003 into 10 to the power minus 3 inch by inch, or it is dimensionless quantity. Now what we will do is that we know that stress in wire BD will be equal to strain in BD multiplied by E. So we will get strain is 1.003 into 10 to the power minus 3, clear, and E is 29 into 10 to the power 3 KSI. You can see, you can take it from the table of mechanical property. So when you calculate it, you will get stress in wire BD will be equal to 29.01 KSI. Now this is the stress, and from property table we can see that yield stress is 36 KSI. So since sigma BD is less than sigma yield of this A36, which is 36 KSI, so it means that this wire is okay, it will not fail. Clear? So the result is valid. Now we will use this formulas, as we know that sigma BD is equal to force in BD divided by area of this BD. Clear? So what we need is that we have stress in BD is 29.01 into 10 to the power 3 KSI, and FBD from equation number 1. This is FBD, which is 2.50 times P divided by area. So diameter is given, so it will be pi by 4 D square, and D is 0.25 square. So when you solve this, you will get this P will be equal to 569.57 pounds, or you can say P is equal to 570 pounds. So this is the answer. This is the amount of load that is applied to this end, causing this point C to move downward of 0.15 inch. And that was all about this problem 3-15. I hope you have enjoyed this video, and this video is dedicated to one of my viewer who requested to solve this problem. I hope you like it. Thank you for watching and subscribing my channel. Welcome back. Problem 4-99. This problem is taken from chapter number 4, Exal loading, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the rigid beam is supported by pin at A and 2 steel wires having diameter of 4 mm. If yield stress for the wire is 530 megapascal and modulus of elasticity for steel wire is 200 gigapascal, determine the intensity of distributed load W that can be placed on the beam and will cause wire EB to yield. What is the displacement of point G for this case? For the calculation, assume the steel is elastic and perfectly plastic. So you can see this is the beam at point A, it is pin supported, and at point B and C there are 2 steel wires of 4 mm diameter that is supporting. There is a distributed load over whole length, which is W. So you have to find this W as well as displacement of this point G due to this load. So you have to find this displacement. So let's start with the solution. So what will be the first step? The first step is that if you remove this pin support at point A, so you will be having a reaction force which is equal to RAY, and if you remove it, so there will be horizontal reaction force RAX. Similarly, if you remove this wire BE, so there will be a vertical reaction of this wire EB on this beam, which is FEB, and similarly for CD, the vertical reaction force offered by this wire CD will be equal to FCD on the beam. So what we will do is that, again, you can see there is a distributed load. So this distributed load, when converted into a point load, so it will be equal to W, the magnitude, into the length over which it acts. So 400 plus 250 plus 180 is 800 millimeter. So 800 millimeter is 0.8 meter, and the unit will be in Newton per meter. Okay. So what we will do is that we will apply equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see the moment about point A, the first moment is due to this FEB, and perpendicular distance is this 0.4 meter, and this is producing counterclockwise, so it will be positive. So I will write FEB or FBE into 0.4. The second moment is due to this FCD, and perpendicular distance is now 0.65 meter, and this is also producing counterclockwise, so it will be positive. So I will write plus FCD into 0.65, and the last moment that is produced due to this W into 0.8, and perpendicular distance is 0.4, and this is producing clockwise, so it will be negative. So I will write minus 0.8 times W into the perpendicular distance is 0.4. So from here what we will get is that 0.4 times FBE plus 0.65 times FCD is equal to 0.32 W. This is your equation number 1. Now we cannot apply any other equilibrium equation because it will not give you our required answer. So what we will do is that we will perform plastic analysis of wires, steel wires. What do you mean by plastic analysis? That the force is producing yield, the force is yield stress, and it is deforming permanently. So what we will assume that both steel wires fail. Both steel wires, okay, let me correct it. This is steel wires yields mean it is deforming permanently. So for that we have been given the yield stress is 350 megapascal. So yield is 350 megapascal, and we know that yield stress is equal to yield force divided by area. So for BE and CD steel wire, the yield forces will be F of BE is equal to F of CD, because both have the same diameter. We will have this formula sigma y into its area. So you have sigma y, which is 350 megapascal. So 530, sorry, this is not 350, this is 530. Correct it as well, 530. So 530 into 10 raised to power 6 multiply by area. Diameter is given as 4 millimeter or 0.04 meter. So it will be pi by 4 times 0.004 square. That will give you force in BE and force in CD. So when you calculate it, both these forces FBE is equal to FCD will be equal to 6.660 kilo Newton. Now you have these forces. This is your equation number 2. So put value of FBE and FCD in equation number 1. So this is your equation number 1. You can see this is your equation number 1. So when you put it the value, so you will get this W. I am not going to put it because this is very easy step. So you will get 21.9 into 10 raised to power 3 Newton per meter. Or you can also convert it is equal to 9.1 kilo Newton per meter. Now you have this value. So what we are going to do is that we will find the displacement of this point B. Clear? So how we will find this displacement? So let's see that. Let me write first displacement. So as wire EB or BE achieve yield stress, so corresponding yield strain will be this one, and we know that this will be equal to yield stress over modulus of elasticity. So you can just put the value. Yield strain is equal to 530 into 10 raised to power 6 divided by modulus of elasticity is given as 200 gigapascal. So 200 into 10 raised to power 9. So when you solve this, you will get this yield strain will be equal to 0.002650 millimeter per millimeter. Now we have this yield strain. So what we are going to do is that we will find the change in length of this wire BE. So we know that strain is equal to change in length or original length. So for BE wire, clear? So this yield strain in wire EB or BE will be equal to change in length of BE divided by original length of BE, clear? So we will find change in length of BE, that will be equal to LBE multiplied by yield strain. So what is the length of BE? So let me check. You can see both have length of 800 millimeter, which is equal to 0.8. So 0.8 multiplied by yield strain, which is 0.002650. So when you solve this, you will get change in length of wire BE will be equal to 2.120 millimeter. Now we have these values. So again, you can see that initially this beam was like this, clear? And due to the loading, this is your point A, this is your point, let's say B, this was your point C, and this is your point G. So due to the loading, the beam will go like this. So this will be the change in length of BE, delta BE. This will be change in length of delta CD, and this will be the change in length of our delta G, displacement of point G. So we know that the distance between A and B was 400 millimeter, or which is 0.4 meter. This distance between B and C was 0.25 meter, and distance from C to G is 0.15 meter. Now what we'll do is that you can see you have two similar triangles, three similar. One is this one, clear? The second one is this one, clear? So we will take this similar triangle. Let's say this is your 1 and this is your 2. So two similar triangle. The first one is triangle, right angle triangle AB1, and other is triangle AG2. So by taking the ratio of their sides, so if I take AG divided by G2, so if AG divided by G2, that will be equal to AB divided by B1. So what we will get is that AG is totally 0.8, clear? So 0.8 divided by delta G, G2 is delta G, that will be equal to 0.4 divided by delta BE, clear? So from here we will get delta G will be equal to 0.8 divided by 0.4 into delta BE, that is equal to 2 times delta BE. Now what we get is that delta G is equal to 2 times delta BE. So put the value 2 multiplied by delta B is 2.120 millimeter. So you will get delta G will be equal to 4.24 millimeter, and which is the answer of our this question. So this was all about problem 4-99, in which we have been asked to find the distributed load, clear, as well as the displacement of point G. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos and help me in growing further. Thank you for watching. Welcome back. Problem 5.115. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and the book name is Mechanics of Material by Beer Johnston, 6th edition. And the topic that we are covering is singularity functions, or it is also known as Macaulay's method. So statement is a beam is being designed to be supported and loaded as shown using singularity function. Find the magnitude and location of maximum bending moment in the beam. And in part B, knowing that allowable normal stress for the steel to be used is 24 kSI, find the most economical wide flange shape that can be used. So you can see this is a simply supported beam with a pin support and roller support at both ends. And there is a distributed load of 3 kips per feet over a length of 15 feet. And there is a point load of 22.5 kips at a distance of 3 feet from point A. So you have to find the location, magnitude, and location of maximum bending moment using singularity function. And then you have to choose the most economical wide flange shape. So let's start with the solution. So first step is that if you remove this pin support, so you will be having a vertical reaction force, that this is AY, and there is a horizontal reaction force which is equal to AX. And if you remove this roller support, so you will be having only vertical reaction, that let this is CY. So first we will find this by using equation of equilibrium. So what we will do is that we will convert this distributed load into point load. So when you convert this distributed load into points load, so you have to multiply this load 3 kips per feet with the total length, which is 12 plus 3, and that is equal to 15, and that is 75 kip. Clear? Now you can apply the equation of equilibrium. So we will apply equation of equilibrium, that sum of all moment about point C is equal to 0, taking the counterclockwise moment as positive. So At this point, see, the first moment is this 75 and perpendicular distance is this is half of 15, which is 7.5, and this is producing counterclockwise movement, so it will be positive. So I will write 75 multiplied by 7.5, 7.5, because it is acting at a distance of half of 15, which is 7.5 feet. And let me correct, is 3 multiplied by 15 is 45, not 75. So this is 45. Okay, the second moment that is produced due to this 22.5 kips load and perpendicular distance is 12 feet, and this is also producing counterclockwise movement, so it will be positive. So I will write plus 22.5 into perpendicular distance is 12. And the last load that is producing movement about point C is AY, and perpendicular distance is 15, and it is producing clockwise, so it will be negative. So minus 15 times AY. The sum of all moment about point C must be equal to 0. So when you solve this, you will get this AY will be equal to 40.5 kips. That is acting vertically upward. Now you can find AX by using equation of equilibrium, that sum of all forces along X direction must be equal to 0, and force toward right side is taken as positive. So only there is a horizontal force AX, there is no other force, so it means that AX is equal to 0. Now we will find this RY by CY by using this equation of equilibrium. So you can see AY, which is upward, that is 40.5 minus this 22.5 kips load, 22.5 kips load minus 45 plus CY is equal to 0. So from here you will get CY will be equal to 27 kips. Okay, now you have all these reaction forces. So what we will do is that we will find shear force equation and bending moment equation by using singularity function. So for that, you can see we have this table that is shown over here. I will show it in the book. This is the table, that is basic load and corresponding shear and bending moment is expressed in terms of singularity function. So what we are doing is that we are only using, we have point load and distributed load. So we are using these graphs for finding, and these are the equation: shear force and bending moment equation for point load, and shear force and bending moment equation for distributed load. So I have copied over here. So let me show you here. You can see I will write shear force equation using singularity function. So starting from this left side, you can see we have vertical reaction force, which is AY, and you can see for the point load, the load is acting downward. So shear force equation is minus P into X minus A power 0, where A is this distance. So for this AY, we have A is equal to 0, and this load is upward. So I will write this V will be equal to AY, which is 40.5 into, this is the equation, X minus A. So A is equal to 0, so X power 0. Now we have this moving from here, we have 22.5 kips load, and this is acting downward. So we will use this equation, but that P will be positive. So plus 22.5 into X minus, now A is here is 3 feet. So I will replace it with 3, and that is power 0. Okay. The other thing is that you can see you have a uniformly distributed load of 3 kips per feet. So this is the diagram, and this is the shear force equation. So this distributed load starts from at a distance of A, and the shear force equation is this one. The load is downward, so this is minus W. So here you can see this distributed load start from the start till the end. Clear? So A is equal to 0 for this. So I will write minus W is 3 kips per feet. So 3 into X minus 0 power 1. And the last term is CY. We will neglect it because we are starting from left side and moving toward, and always you have to neglect the last term because this will give you 0. If I include it, so I will write plus CY into X minus A. X minus A, and A is total 15 because this is acting at this point. So this is A. So that is 15 feet. So that is power 0. Again, you can see that for X is less than or equal to 15, this term will become 0 because anything that is negative inside this Macaulay bracket will be considered as 0. So if X is less than 15, this term will be 0, or X is equal to 15, this term will become 0. So we will neglect this. Let me remove this. That is only for your understanding purpose. Now we will going to find the bending moment equation. So bending moment equation using singularity function. Okay, so let me write it over here. So this bending moment equation will be equal to, now starting again from the left side, you have AY load. So the moment equation is this one. For this load is downward, this is negative, so I will write positive. So AY is 40.5 into X minus A. So for this AY load, A is equal to 0 because it is starting from the start. So this power 1. Now the second load is again 22.5. So I will write plus 22.5 into x minus a is 3 feet, so 3 power 1. The third load is distributed load, which is 3 kips per feet. So for distributed load, you can see the moment equation is this one. So minus 1 over 2 w naught is 3 into x minus a. So a is equal to 0. So x minus a power x minus 0 power 2. Okay. So we can write this equation as 40.5 x minus 3 over 2 into x square plus 22.5 into x minus 3 power 1. So this is equation number 1, which is for shear force, and this is for bending moment. Now in our first part, we have been asked to find the magnitude and location of maximum bending moment. So you have to find the maximum bending moment, and we know that maximum bending moment, I will write it, maximum bending moment occurs where shear force is equal to 0. So what we will do is that put V is equal to 0 in equation 1. So we will see that this is 3 feet distance from point A to B, clear? So for x is greater than 3 feet, x is greater than 3 feet and less than 15 feet. There is a point where the shear force will be equal to 0. Let this point is xd. So we will find it xd is greater than 3 feet and less than 15 feet. So maximum bending moment occur where shear force is equal to 0. So we'll put it in this equation, which is V is equal to 40.5, because x power 0 is 1 plus 22.5 into x minus 3 power 0 minus 3x. So we will put it V is equal to 0. So it will be equal to 40.5. This plus 22.5, this term will also be equal to 1, because anything power 0 is 1. So minus 3, we will replace this x with d, because we are going to find the distance at which shear force is equal to 0. So from here 3xd is equal to 40.5 plus 22.5, and xd will be equal to, this is 40.5 plus 22.5 is 63. So 3 into xd is equal to 63. I think we have made any mistake. Let me check it over here. This is correct, because the load is upward. This load is 22.5 is downward. So you can see this equation is minus p into x minus a power 0 for downward. So it should be negative. So let me correct it. This is negative, and this is also correct. So here we will also rectify. This is also negative, because you can see this w is this 22.5 load is acting downward. So for downward we have minus p into x minus 1. Okay, so what we will do is that this will also negative. Okay, so this will be negative, and this will be also negative. That will be equal to 18. So from here you will find the location of the point D, which is 6 feet from the start, and at this point at a distance of 6 feet, there the shear force will be 0, and we will get the maximum bending moment. Now put xd is equal to 6 feet in equation 2. So we will get maximum bending moment, that will be equal to 40.5. X will be replaced with xd 6 feet minus 3 over 2 6 square plus 22.5 into x 6 minus 3 is 3. Clear? So when you solve this, you will get the maximum bending moment will be equal to 1 to 1.5 kips into feet. And if you want to convert it into inch, so 121.5 into 12 will convert this kip into inch. So the value of maximum bending moment will be equal to 1458 kip into inch. So this is the answer of our first part. These two are the answer of our first part. Now we will move towards second part, and second part is that find the most economical wide flange that can be used. And we have been given allowable stress is 24 ksi. So let me write it. We have allowable stress is 24 ksi. We have maximum bending moment that we have calculated here is 1458 kip into inch, and we have to find most economical wide flange beam. Okay, so we know that allowable stress is equal to maximum bending moment divided by minimum section modulus. So from here we will get this minimum section modulus will be equal to maximum bending moment divided by allowable stress. So put the value of this maximum bending moment and allowable stress. So 1458 divided by 24 ksi. So 24, when you divide it, so you will get 60.75 cubic inch. So this is minimum section modulus. Now what we will do is that we will go to the table that is given at the end of book. I will show you at the end of book, you have to go to the wide flange beams, property of rolled section, and then you have to choose the US customary. Clear? So let me choose a pen. Okay, so you can see this is the section modulus. So the value was 60.75. So that we will choose those beam which are near to 60.75. So one thing is that you can see this is nearest to 60. So W 21 into 44. 21 into 44. So I will write it. The first one is W 21 into 44 having section modulus is 81.6 cubic inch. This is section modulus. This is beam, W beam. So we have one option is this. Now we'll move toward another one. The second one is, you can see here is, this one is closer. I think there is a problem. Okay, you can choose it. I will write some of the values which you can see 18 by 50. It will have 88.9 cubic inch. The third one is W 16 by 40. That is 64.7 cubic inch. The fourth one is W 14 multiplied by 43 having section modulus 62.6 cubic inch. The fifth is W 12 into 50. That is having 64.2. The sixth is W 10 into 68 having 75.7 cubic inch. In this way, you can have many options for selecting wide flange beam, but we have been asked to find the most economical wide flange beam. So you can see the most nearest value is this one. Clear? This is the most nearest. But in this W 14 into 43, this is pounds per feet. This is the weight of this beam. Pound in 14 pounds per feet. So we have to select a lesser weight. And among all these options, so you can see this W 16 into 40 is having smallest weight per feet, and its section modulus is 60.4, which is also greater than the minimum section modulus. So what we will choose? We will choose W 16 by 40 is the economical wide flange beam for the loading shown, and allowable normal stress is 24 kSI. So this is the answer of our question. And that was all about this problem 5.115. I hope you like that and you have learned it. Always remember that while solving this problem, you have to be very careful, because a small mistake can put you in trouble. If you have any question, you can ask me in comment section. And if you have any problem related to the singularity function, you can tell me. I will share you the link of that lecture that I have explained in detail, and you will definitely find it interesting and knowledgeable. Again, thank you so much for subscribing my channel and liking me. Welcome back. Problem 5.99. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and the book name is Mechanics of Material by Beer and Johnston, 6th edition. And the topic is singularity function or Macaulay's method. So statement of the problem is, using singularity function, write the equation defining the shear and bending moment for the beam and loading shown. And in B part, use the equation obtained for moment to determine the bending moment at point C, and check your answer by drawing the free body diagram of entire beam. So you can see this is a cantilever beam having fixed support at point C, and there is a distributed load from A to B, and that is magnitude W naught. So you have to find the shear and bending moment equation by using singularity function. So let's start with the solution. So as you know that we have this table that is shown over here for bending moment and shear force diagram by using singularity function. And in this diagram, we can locate that this is the diagram for distributed load. And from here, you can see the distributed load start from here till the end. Clear? But here, this is starting from the point A and till point B. So we have to make it till the end. So what we will do is that we will proceed it further, and we will add this W naught through entire length of the beam, and then we will subtract it the same downwards in order to cancel its effect. This is W naught. Now we will apply this singularity function. So you can see this is the equation for this distributed load, which is W of X, and that is equal to, for this entire W naught, you can see here A is equal to 0 because it is starting from point A. So this equation will be equal to W naught into X minus A is 0, so X power 0. Now for this distributed load, you can see that this distance from A to B is small a. So what we will do is that we will write minus. Why minus? Because this load is upward, and here this load is downward. So for downward, this is positive, and for upward, it is negative. So I will write W naught into X minus A power 0. So we will get this W is equal to W naught minus X power 0 is 1. So minus W naught into x minus a power 0. And we know that this W, we know that dv over dx is equal to minus w. So from here, this w will be equal to minus dv over dx. So we will put the value of w is equal to w naught minus w naught into x minus a power 0. So what we will get is that if I take dv is equal to minus w naught into x minus a power 0 into dx, and if we integrate it on both sides, so we will get shear force will be equal to minus w naught x, and that will be equal to plus w naught into x minus a power 1, which will be the shear equation. This is equation number 1. Also, we know that dm over dx is equal to shear force. So from here, this shear force into dx will be equal to dm. So I will write dm is equal to, this shear force equation is minus w naught into x plus w naught into x minus a power 1, and dx is there. So if you integrate it on both sides, so you will get the equation of moment that will be minus w naught x square divided by 2 plus w naught into x minus a power 2 divided by 2. Clear? And this will be the equation of moment. This is one method you can get the equation of shear force and bending moment. Second thing is that you can use this diagrams or graphs in order to get the shear force equation and bending moment equation. So let's use it as well. We will see, we will get the same answer. Now here you can see shear force equation is this one. So for the loading that is shown about for w naught, so it will be equal to minus w naught into x minus a. A is 0, so x minus 0 power 1. Plus, now this load is upward. Clear? So for that it will be plus for upward. Plus value for upward. So I will take w naught into x minus a power 1. So what we will get is minus w naught x plus w naught into x minus a power 1. So you can see this is the, okay, this is the equation. You can compare it with the equation 1. You can compare this equation and this equation, both are same. Similarly, you can also find moment equation. So moment equation is this one. Clear? So for this uniformly distributed load of w naught, so I can write minus 1 over 2 w naught into x minus a. A is 0, so x square plus 1 over 2 y plus, because this w naught is upward now, so it will be plus into x minus a power 2. So you can see this is the equation. This equation and this equation both are same. So you can try any of the methods. So this was our first part. We use singularity function in order to define the shear force equation. Clear? And then bending moment equation, which is this one. Now we will move towards second part, and in second part use the equation obtained for m to determine the bending moment at point C. So what is C? C is here. So here x is equal to 2a. So put, this is your part B. Put x is equal to 2a in equation 2. So we will get this m is equal to minus w naught 2a square divided by 2 plus w naught into 2a minus a whole square divided by 2. So it will be minus w naught 4a square over 2, and that will be equal to w naught a square over 2. So moment will be equal to minus 2 w naught a square plus w naught a square over 2. So if you take the LCM, that will be 2 and there is 1. So divide 2 by 1 is 2 and multiply it with minus 2. So minus 4 w naught a square plus 2 divided by 2 is 1, multiply by w naught into a square will be w naught a square. Okay, if you further simplify it, it will be equal to minus 3 w naught a square over 2. This is the equation of the moment. Clear? And that is the answer. Now the last part is that it has been given that check your answer by drawing the free body diagram of entire beam. So what we will do is that we will draw the free body diagram of entire beam. So there is a distributed load from point A till point B. Clear? And that is given as w naught. This is point A, this is point B. This is distance A. And from B to C, the distance is also A. So when you remove the fixed support at point C, this is C. So you will be having a vertical reaction that is equal to RC, as well as you will have a moment MC. Clear? And there will be a horizontal reaction force as well, but that is equal to 0 because there is no horizontal component. So we will write sum of all forces along x direction must be equal to 0, and force toward right side is taken as positive. So RCX will be equal to 0. It means that RC is equal to RCX, horizontal component is equal to 0. The second thing is that we will apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So this is distributed load when converted into point load. So it will be W naught and it will be multiplied by the length over which it acts, and it acts at a distance of A by 2 from either side. Now we will apply this equation. So we have one force minus W naught into A, which is acting downward, and other force is plus RCY, so is equal to 0. So from here we will get RCY will be equal to W naught into A. And the last thing is that you will apply the equation of equilibrium, that is sum of all moment about point C is equal to 0 and taking the counterclockwise moment as positive. So here you can see one moment is counterclockwise, that is minus MC, and the second moment about point C is this W naught into perpendicular distance is 3A divided by 2, because A plus A by 2 is equal to 3A divided by 2, and this is producing counterclockwise movement, so it will be positive. So I can write plus W naught into A into 3A divided by 2 is equal to 0. So moment about point C will be equal to 3W naught A square over 2. Okay, so this is the moment at point C by using equation of equilibrium and from the free body diagram of the beam. So you can see here this is positive, so it means our assumed direction is correct. And from this shear bending moment equation using singularity function, here when you put it the value of x, so you are getting this minus 3W naught into A. So this means that this is correct. Why? Because negative means if you remove this, so moment will be equal to 3W naught A square over 2, and that means this is clockwise direction. So you can see from this and this we are getting the same answer and same direction. So this is all about this problem 5-99. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-139 that is taken from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the curved beam is subjected to a bending moment of 40 pounds into feet. Determine the maximum bending stress in the beam. Also sketch a two-dimensional view of the stress distribution acting on section AA. So you can see this is the curved beam, clear, that is acted upon by this moment M, and which is given as 40 pounds into feet. So due to this moment, you have to determine the maximum bending stress in the beam. So let's start with the solution. So here you can see I have written the formula that is used in curved beams. The first one is this one, second one is this one, and third one is this one. So in this formula, sigma is equal to normal stress or bending stress. M is the moment that is given. What is this capital R? So capital R is distance from this center of curvature till to the point where its neutral axis lies. So this distance is R. We will find this clear. What is this small r? So small r is distance from the center of this curvature to the any point. It can be here, it can be here, it can be anywhere. So where you want to find the stress, and this r dash will be equal to distance from this center of curvature till the centroid of this section. So we'll find them each by each. So let's start with the finding radius r dash, which is the distance. I will write it distance from center of curvature to the centroid of section. Clear? So we'll find that. What is the center of curvature? So you can see this arc is bent in a curve and it is forming an arc having radius is 3 inch. So this is center of curvature. So what if I extend this center of curvature, our x is passing through this center of curvature, and let's take this as a reference line in order to find the centroid of this section, which is T section. So for that I will write the formula. This r dash will be equal to sum of y dash into A divided by sum of area. So this is your first this first rectangle is your part 1 and this second rectangle is your part 2. So from this we will get y1 dash into A1 plus y2 dash into A2 divided by sum of area, which is equal to A1 plus A2. And what is area A1? So I will write it. A1 is equal to, you can see here, this is 2 and this is 0.5. So 2 multiplied by 0.5 square inch. What is area A2? So area A2 is, you can see this height is 2 and this width is 0.5. So it will be again 2 into 0.5 square inch. Now what is y1 dash? So y1 dash is distance from this reference line or from the center of curvature till the mid of this first section. So you can see we have to find this distance, which is y1 dash. And this y1 dash, you can see that this distance is equal to, this is 3 inch. So 3 inch plus 2 inch, 5 inch plus 0.25. So this will be equal to 5.25 inch. So I will write it, y1 dash is equal to 5.25 inch. 5.25 inch. Now what is y2 dash? So y2 dash is distance from this centroid of section of curved beam till the mid of second section. So this distance is already, you can see this is already 3, clear. So 3.5 of 2 is 4. So this distance is 4 inch, and I will write it here. This is equal to y2 dash, and this, that is equal to 4 inch. Okay, now 4 inch. Now I put all these values in this formula. So R dash will become equal to y1 dash is 5.25 multiply by 2 multiply by 0.5, which is area A1, plus y2 dash is 4 inch into area A2, which is 2 multiply by 0.5, divide by, I will write 2 multiply by 0.5 plus 2 multiply by 0.5. So when you solve this, you will get this R dash, which is distance from center of curvature to the centroid of section, comes out to be 4.625 inch. This is this R dash. Okay, now I will remove these things. So in order to have a clear understanding about what is R dash, so let me plot it. So R dash is distance from neutral axis till the mid of, distance from the center of curvature till this centroid. This is the centroid. So this distance is R dash. Distance from the center of curvature till the centroid of this section is R dash, and this R dash is 4.625 inch. Now we will move toward finding second term, which is capital R. So capital R, you can see it is equal to area divided by integral of dA over R for the entire area. So what is the area? Total area. So total area A is equal to A1 plus A2, which is equal to 0.5 multiplied by 2 into 0 plus 0.5 multiplied by 2. So 1 plus 1 will give you total area will be equal to 2 square inch. Okay. Now the second term here is this one. So I will write integral of dA over R for the entire area. So you can see these two portions are rectangle 1 and 2, and they are away from this reference line. So for that we will take the value of this from this table. Since our shapes are rectangle, so this line is the axis passing through curvature. So you can see that from this axis the rectangle is locating at a distance of R1 from this and R2 from this, having width or breadth is equal to B. So as we have two triangles, so first the formula is, the general formula will be equal to B into ln of R2 over R1. But as we have two sections, so I will write integral of dA A over R. This is not dA, this is A. This is A. Okay. For the first section, let me show you here. You can see this is the centroid axis passing through this center of curvature. So for that, for section 2, let's take section 2 first. So for section 2, this will be equal to R1. So R1 is 3 inch. You can see 3 inch, and R2 is distance from this center of curvature till the top layer. So this is equal to 2. 2 plus 3 is 5. So R1 is 3 and R2 is equal to 5. So I will write it, and the width is 0.5 for this. So I will write the B is equal to 0.5 ln of R2 was 5 and R1 was 3. So this is for first section. Now we will move toward the second section, which is this one. So for that, R1 will be this one, which is equal to 5, and R2 is this one, which is equal to 5.5 inch. And breadth here, you can see the breadth of this section is 2. So I will write plus 2 into ln of 5.5 divided by 5. So when you solve this, this will give you 0.44603 inch. Now you have both the values. You can just plug it in this formula, which is equal to R, and area is 2 divided by this integral of dA over R for the entire area is 0.44603. So when you solve this, you will get this 4.480 inch. Now what is this R? It is the distance from the centroid till the neutral axis of this curved beam, because in curved beam the neutral axis does not pass through the centroid. So this will be R. So you can see this R is 4.480, and which is below from this centroid. So let this distance is capital R. I will write it over here. This capital R is equal to 4.4840 inch. Okay. Now we will find, you can see we have find out this capital R, we have find out this R dash and R clear. So we'll find this E. So E will be equal to R dash minus R. So R dash is how much? R dash is this 4.625 minus R is 4.480. So when you solve this, you will get this is equal to 0.1410 inch. Now each and every value is available except this R. This R, I have already told you that this is the distance from this center of curvature to the any point where you want to find the stress. It can be anywhere like this. And since we have been asked to determine the maximum bending stress in the beam, so maximum bending stress will either occur at this point or at this point. Like this point is point A and this point is point B. And you can see due to this movement, the beam will straighten up and this top portion will become in compression. Clear? This top, due to this movement, this upper one will be in compression and this bottom one will be in tension. Okay, now what we will do is that we have been given the bending moment here, so just plug it in this formula. This is the formula. So for point A, which what is point A? Point A is this A. So this distance will be equal to RA. This is your point A and this is your point B. So this is equal to RA. So first we will find the allowable bending stress for point A. So for point A, RA is equal to how much? RA is equal to 3 inch plus this 2 plus 0.5, which is 5.5. I will write RA is 5.5 inch. And since point A is in compression, so I will write sigma A is equal to M into capital R minus RA divided by E into RA. So put the value. M is equal to how much? That is given as 40 pounds into feet. So we will convert this 40 pound into feet into 40 multiplied by 12 will convert it into 40 multiplied by 12 will convert it into pound into inch. So this is the value of movement. What is capital R? Capital R is 4.480 minus this RA. RA is 5.5 divided by area. Area is 2. What is E? So we have calculated E. Where is E? Where is E? E is here. This is E. This is E. So 0.1410 multiplied by RA is 5.5. So when you solve this, you will get stress, normal stress at point A come out to be 314 psi. So this is equal to 314 psi, and it means that point A is in compression. Negative sign shows that point A is in compression. Now we'll move toward finding the bending stress for point A, B. So bending stress for point B, which is in tension. So the formula sigma B will be equal to M multiplied by capital R minus RB divided by A into E multiplied by RB. What is RB? So RB is distance from center of curvature till this point B, which is equal to 3 inch. Clear? So I will write RB is equal to 3 inch. Rest all values are available. Moment was how much? 40 pound into feet. So 40 multiplied by 12 will convert the unit into pound into inch. Multiplied by R, capital R was 4.480 minus RB is 3 divided by area was 2. E was 0.1410 multiplied by RB is 3. So when you calculate it, you will get stress at point B comes out to be 842 psi. Since the value is positive, so it means that point B is in tension. Okay. So these are the answers of our this question. Now in second part, it is given that sketch the two-dimensional view of stress distribution acting on section AA. So this is section AA. So I will take this section AA. So this is section AA. And you can see the rest of the portion of this will be like this. And we again know that this R dash, capital R, is distance from this center of curvature till the neutral axis is 4.480. So let this is your 4.480. This is the location of neutral axis. Clear? So about neutral axis, we have seen that point A was in compression. Clear? And point B was in tension. So I will draw this for point A. This top portion was, this is sigma A, which is 314. So this will be 314 psi. And this is neutral axis. So in curved beam, it will follow a hyperbola. Clear? So this will, and at this is your point A. At this is your point B. So at B, the bending stress was 842 psi, and it will be in tension. So this hyperbola will follow like this. Clear? And you can see this member is in compression and this will be in tension. Okay. So this is the sketch or stress distribution acting on section AA. And that was all about this problem 6-139. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 11-93. This problem is taken from chapter number 11, Energy Methods, and book name is Mechanics of Materials by Beer Johnston. It's its 6th edition. And the topic that we are covering is Castigliano theorem. So statement is for the beam and loading shown, determine the deflection at end C, use E is 29 into 10 to the power 6 psi. So you can see this is a cantilever beam having fixed support at point A, and at point C we have 4 kips load, and at point B we have 8 kips load. So this is wide flange beam. This is, you can see, W14 by 30, a wide flange beam. So what, due to this loading, the beam will deflect like this. So we are going to find the deflection at point C, which is delta C or YC. So we will apply Castigliano theorem, and by using Castigliano theorem, which states that deflection with respect to any point, if you are using to find the deflection due to this force or this force, so you can find it by using the partial derivative of total strain energy with respect to that force. For example, if that force is Q, or if that force is P, so you can find that by using the partial derivative of total strain energy with respect to that force. We know that strain energy due to bending, which is equal to capital U, and that is equal to integral of m square over 2EI into dx. Clear? So what we are going to do is that we will find the moment equation for portion BC. I will write it portion BC, which is for x is greater or equal to 0 and less or equal to 2 feet, and we will find the moment for portion AB, where this x is greater or equal to 2 feet and less or equal to 8 feet. So what we will do is that, again, we know that if you take the partial derivative of total strain energy with respect to that force, which is let that is Q, which will give you the deflection at that point, and we are going to find at point C. So deflection at point C will be equal to partial U or partial Q, and if you take the partial derivative of that total strain energy, so you will get 1 over EI, and that will be integral of m into partial m over partial Q into dx. So this will be the equation of deflection for the strain energy. So here you can see we will use this equation. For that we will need the moment, bending moment for portion BC as well as for portion AB. So what we will do is that we will find for portion BC. Clear? And what we are doing is that if we cut the beam in portion BC and let this distance is x and draw the free body diagram, so it will be like this. This is your point C, where 4 kips load is applied, and we will replace this force with Q. Let this Q is equal to 4 kips and this distance is equal to x. So when you cut it, you will be having a shear force and you will be having a moment M. So we are interested to find this moment M. Okay. This is point, let this point is point O. So what we will do is that we will apply equation sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about point O, the one moment is 4 into x, and this is producing clockwise, so it is negative, and the second reaction moment is M, which is also clockwise, that will be also negative. So I will write minus M minus Q times x. For time being we replace 4 with Q, so Q multiplied by x, Q into x is equal to 0. So it means that this moment is equal to minus Q times x. Okay, now we have this moment. So here we also need another term, that is implies that partial M over partial Q will be equal to minus x. So now you have this M as well as you have this term, so you can just put it in this. Okay, so what we are going to do is that we will find this term integral from 0 to 2 feet, and M into partial M over partial Q into dx. This will be equal to integral from 0 to 2 feet. M is equal to minus Q times x, and this partial M over partial Q is minus x into dx, which will give you minus qx square into dx. And if you integrate it again, so what we will do is that it will be equal to minus Q integral of 0 to 2 feet, and it will be x square into dx, which gives you, if put Q is equal to 4 kips, so that will be equal to minus 4 into x cube by 3, and limit will be from 0 to 2 feet. Clear? So that will be equal to minus 4 by 3 x cube 0 to 2 feet. So minus 4 divided by 3, and that is 2 cube minus 0 cube. So when you calculate it, it will be equal to 10.67 kips into cubic feet. Now we just only find this term here for portion BC. What we will do is that we will find this the same thing for portion AB. So what we will do is that we will cut this beam anywhere this distance will be equal to x there, and we will draw the free body diagram. So let me draw it first. This is your point C, where you have 4 kips load, and that is taken as Q. Clear? And at point B, let this your point B, where you have 8 kips load. Clear? The distance between A to B to C is 2 feet, and total distance is taken as x. X is variable. Clear? So when you cut it, you will be having a shear force V, and you will be having a moment. And what will be x is greater or equal to 2 feet and less or equal to 8 feet. Okay. Now we will find this moment equation by using sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So you can see about point 1 moment is this Q into perpendicular distance is x. This is clockwise, so it will be negative. So I will write it minus Q times x. The second moment is due to this load into perpendicular distance is this one, which is equal to x minus 2 feet. And this is also producing clockwise, so it will be negative. So I will write minus 8 into x minus 2. This distance is x minus 2 feet. Okay, and the third moment is this one, which is the reaction moment, and this is also clockwise, so minus m. Their sum must be equal to 0. So it means that this moment will be equal to minus 8 into x minus 2 minus q into x. That this is your equation number 2. Okay, now we have the equation from limit from the limit was from x is greater than 2 and less than 8 feet. Okay, so 2 and 8. So it moment into partial m over partial q into dx. So again put it limit from 0 to 8. So plug in the value of m and delta m, partial m over partial q. So m is minus 8 into x minus 2 minus q into x. This is the value of m, and delta m is minus x into dx. Put q is equal to 4 kips. That is we have taken over here. So what we will get is this integral of 0 to 8. It will be minus 8 into x minus 2 minus 4x into minus x into dx. So when you multiply this minus with this both term, so I will write it, it will be equal to 8 into integral from, this is 2 to 8, not 0 to 8, 2 to 8, 2 to 8, and that will be equal to x square minus 2x into dx, and this term will be minus 4 into integral from 0 to 2 to 8, and this term will be x square into dx. Now this 8 into x square, so 8x square, 8 into integral of 2 to 8 dx minus 16 into integral of 2 to 8 dx and minus 4 into integral 2 to 8x square dx. So this will give us 8x cube by 3 and limit from 2 to 8 minus 16 into x square. Here there is x square over 2 and limit will be 0 to 8 minus 4x cube over 3 and limit will be 0 to 2 to 8. So when you solve this, this will, after taking the limit, this term will give you 4096 divided by 3 minus these terms will give, all these terms will give, I will write it, you can also check it later, 1024 divided by 2 plus 64 over 2 plus 2048 by 3 minus 32 divided by 3. So this will give us the term, this integral from 2 to 8 m into partial m over partial q into dx will give us 1536 kip into cubic feet. Now what we do is that we will find deflection at point C. So deflection at C is equal to 1 over EI into integral from 0 to 2 m partial m over partial q into dx plus 0 to 8 m into partial m over partial q into dx. It will be sum of both these. So just put the value 1 over EI. Again this term we can see that this term is equal to 10.67. So 10.67 plus this term which we have find out here, you can see this is, which is 1536. Clear? This is equal to deflection at point C. So we have E is given as 29 into 10 raised to power 3. Let me check, 29 into 10 raised to power 3 KSI. So we do not have I. So what we will do is that again you have to go to the property table of this rolled steel, and here you can see that you have to search for W 14 by 30, that is given. So here you can see I is 291 inch power 4. So I will write the value 291 inch power 4. Okay, so these two terms having units kept into cubic feet. So what we will do is that this is inch power 4. So we will find this EI. So EI is 29 into 10 raised to power 3 KSI. Clear? And it is multiplied with 291 inch power 4. That will give you 8.439 into 10 raised to power 6 kip into inch square. We know that 1 feet is equal to 12 inch. So 1 inch is equal to 1 over 12 feet. So it is square. So 1 inch square is equal to 1 over 12 square into square feet. Okay. So again, we will multiply this 8.439 into 10 raised to power 6 with this value of 1 over 12 into 1 over 12 square. So you will get the value in 58.604 into 10 raised to power 3 kips into square feet. Now these are also into kips into cubic feet, and this is kip into feet square. So what we will do is that YC is equal to 10.67 plus 1536 having unit kip into cubic feet, and EI is 58.604 into 10 to the power 3 kip into feet square. So at the end, what we will get is that we will get this deflection at point C will be equal to 0.0264 feet. And we know that 1 feet is 12 inch. So if you multiply it with 12, 1 feet is equal to 12 inch. So you will get the value is 0.317 inch. YC, which is 0.371 inch. And this deflection will be downward. And this is the answer of our this part. So I will conclude it. We have find the deflection of this point C at point C by using Castigliano's theorem, which state that the deflection can at any point can be obtained by taking the partial derivative of total strain energy with respect to that force. So here we take this Q at point C is equal to Q, which is 4 kips, and we applied this equation in order to get our required deflection. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem example 1.8 that is taken from chapter number 1 stress, and the book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is member AC shown in figure 1-18A is subjected to vertical force of 3 kilonewton. Determine the position X of this force so that average compressive stress at smooth support C is equal to average tensile stress in the tie rod AB. The rod has a cross-sectional area of 400 square millimeter and contact area at C is 650 square millimeter. So this is member AC, clear, that is subjected to a point load of 3 kilonewton. There is a tie rod AB which is in tension, and this point C which is in compression. So you have to determine this X for which the average normal stress in tie rod due to tension will be equal to average normal stress due to compression at C. So let's start with the solution. So first step is that we will remove this tie rod and the reaction force by the C, and we will draw the free body diagram I have shown over here. You can see that it is given that tie rod AB is in tension. Clear. As a result, this tie rod will exert a vertical force upward on this member AC. So I have represent this as FAB, and point C is in compression. So as a result, this support will apply a vertical force FC on this member, which is already shown here. So here three values are unknown: FAB, FC, and X. So we'll find them by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see FAB, which is upward, so it is positive. Clear. 3 kilonewton force is downward, so minus 3 kilonewton. So in Newton it is 3000 Newton, and plus FC, which is also upward. So their sum must be equal to 0. So I will write FAB plus FC minus 3000 Newton is equal to 0. This is your equation number 1. Now we'll apply another equation of equilibrium, that sum of all movement about point A is equal to 0, and taking the counterclockwise movement as positive. So about point A, first movement is due to this 3000 Newton force, and perpendicular distance is X. It is producing clockwise movement, so it will be negative. So I can write minus 3000 multiplied by X. The second movement is due to this load, which is FC, and perpendicular distance is this 200 millimeter, and it is producing counterclockwise movement, so it will be positive. So I can write plus FC into 200 millimeter is equal to 0, and this is your equation number 2. Now in equation number 1, FAB and FC are unknown, so we cannot find this, and in equation 2, FC and X are unknown. So we will find this unknown by using a third equation. So let me write it. The statement was given for average normal stress. So let me also tell you, it is given that the average compressive stress at smooth support C, average compressive stress at C is equal to the average tensile stress in tie rod. So average tensile stress in tie rod. Clear? So what is average normal stress at C? So it will be equal to, definitely it will be equal to force at C divided by area at C, and average normal stress in tie rod is equal to FAB divided by area of AB. So put the values in this equation. So we do not have FC, so FC divided by its area at contact C is equal to 650 square millimeter. So I can write 650 square millimeter is equal to FAB, which is also not known. So FAB divided by area, cross sectional area of AB is 400 square millimeter. So 400 square millimeter. So from this, what we will get, this FC will be equal to 650 divided by 400 multiplied by FAB. And when you solve this, you will get this FC will be equal to 1.625 times FAB. This is your equation number 3. Let this is your equation number 3. Now put value of FC in equation number 1. So when you put it, FAB plus FC will be replaced by 1.625. FAB minus 3000 will be equal to 0. So 2.625 FAB will be equal to 3000 Newton. So FAB will be equal to 3000 divided by 2.625. So when you solve this, you will get FAB will be equal to 11143 Newton. Now what we will do is that put value of FAB in equation number 1. What is the equation number 1? So equation number 1 is this one. So you will get 1143 plus FC minus 3000 will be equal to 0. So from here you will get FC will be equal to 1857 Newton. Now you have this FC, clear? So what we will do is that you can just put the value of this FC in equation number 2. So I will write it, put the value of FC in equation number 2. And equation number 2 is minus 3000 into X plus FC into 2 plus FC, which is 1857 multiplied by 200 is equal to 0. So minus 3000 X plus 1857 into 200 is equal to 0. So it means that 3000 X is equal to 1857 multiplied by 200, and X will be equal to 1857 multiplied by 200 divided by 3000. So when you solve this, you will get X will be equal to 124 millimeter. So this is the value of X is equal to 124 millimeter when a load of 3 kilonewton act at a distance of 124 millimeter from point A, and it will result that average normal stress, tensile stress in tie rod AB will be equal to the average normal compressive stress at the smooth contact surface at point C. And that was all about this problem, example 1.8. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Example 6-1. So statement is draw the shear and moment diagram for the beam shown in figure 6.4a. So you can see this is a simply supported beam that is acted upon by a uniformly distributed load of W. Clear? The length of this beam is L. So let's start with the solution. So first step is that if we remove this support, so there will be a reaction force. Let this is RA, and if we remove this roller support, so we will have a reaction force that is represented as RB. So we'll find this reaction force RA and REB by using equation of equilibriums. So how? So let's move. And so first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So first moment due to force is RA and perpendicular distance is L, and that is producing moment about point B, and this is clockwise. So I will write it minus RA into L. The second moment that is produced by this distributed load, and this distributed load when converted into point load, so it will be W into L, and that will be acting at a distance of L by 2 from both sides. Clear? And that will also produce a counterclockwise moment, and that will be positive. So I will write plus W into L by 2 is equal to 0. I will also show this load, distributed load when converted into point load, so it will be W into L, and that will be L by 2. Now if you solve this, so you will get RA into L is equal to WL square over 2. So from here you will get RA will be equal to WL over 2. So this is your reaction force at point A. Now we'll move to another equilibrium condition, that sum of all forces along y direction must be equal to 0 and force taken upward as positive. So you can see we have three forces. One is RA, the second is RB, and third one is W into L. Their sum must be equal to 0. So RA, which is W into L over 2, minus this one, which is W into L, plus RB is equal to 0. So again from here you will get RB minus WL over 2 is equal to 0. So from here you will get RB will be equal to WL over 2. Now you have both the reaction forces RA and RB. So we'll move and we will section the beam at any point. So if we section the beam at any point and draw the free body diagram, so for X is greater or equal to 0 and less or equal to L. So if I cut the beam and draw its free body diagram, so definitely here we have RA, which is WL over 2, and we have our distributed load which have magnitude W, and when we convert it, it will give you W, and let this distance is X where we have cut this beam, so it will be W into X. And when you cut it and at any distance, so there will be a shear force and reaction moment, and let this is M and this is 0.1. So we'll find this shear force and bending moment. So how will, so first equilibrium condition is sum of all forces about y direction must be equal to 0. So you can see that we have three forces. One is this one, the other one is this one, and third one is shear force. Their sum must be equal to 0. So I will write WL over 2 minus W into X minus V is equal to 0. So from here you will get V is equal to WL over 2 minus W into X. And if you take W as common, so we will have W into L by 2 minus X. This is the shear force equation for the range X is greater than 0 and less or equal to L. Now we'll find the moment. So sum of all moment about 0.1 is equal to 0 and taking the counterclockwise moment as positive. So first moment is due to WL over 2 and perpendicular distance is X, and it is producing clockwise about this 0.1. So I will write minus W into L over 2 and perpendicular distance is X. The second moment is due to this W into X, and that will be acting at a distance of X by 2 and it is producing counterclockwise movement, so it will be positive. So plus W into X into perpendicular distance is X by 2, and there is external moment and their sum must be equal to 0. So from here you will get moment is equal to WX square over 2 plus WX square minus WX square over 2 plus WLX over 2. Again, if you take W over 2 is common, so you will get LX minus X square. This is the moment equation. Now you have both the moment and shear force equation. Equation 1 is shear force equation, while equation 2 is bending moment equation. So with the help of this equation, we will draw the shear force and bending moment diagram. I will copy it. And I will paste over here so that we can easily draw the shear force and bending moment diagram. So we'll write equation 1 over here. V is equal to W into L by 2 minus X. So we have both these two equations. So for shear force diagram, I will draw vertical lines from the end of the beams, and along horizontal line there will be the length of the beam, so shear force. Now you can see at this point you have a reaction force which was WL over 2, and there is also reaction force which was WL over 2. So at this point at X is equal to 0, or you can simply, you have this equation, so you can put, this is equation number 2 and this is your equation number 1. So for X is equal to 0, put in equation 1, we will get V is equal to WL over 2. You can say that when X become equal to 0, so this equation will be WL over 2. Now for X is equal to L by 2. So when you put X is equal to L by 2 in this equation, so this term will be equal to 0, so it means V is equal to 0. So shear force will be equal to 0. For X is equal to L, so put in equation 1, V will become equal to minus WL over 2. So you can put, so you have three values, this one 0 and this one at. So at X is equal to 0, we have V is equal to W. Let this 2 division, this is WL over 2. At X is equal to L by 2, let this is, for example, this length is L by 2. Clear? So we have shear force 0. At X is equal to L, we have shear force is minus WL over 2, which is this point. Now you can see that this load is a horizontal load, so shear force be 1 degree higher, and it will be a straight line with slope decreasing. So you can join these 3 points by using a straight line. So this will be your shear force diagram. Now for bending moment diagram, again I have to draw a horizontal line, and here we will take the bending moment. Now for X is equal to 0, put in equation 2. equation 2. Equation 2 is this one. So when x is equal to 0, so this whole moment will be equal to 0. For x is equal to L over 2, when you put it in equation number 2, you will get moment is equal to WL square over 8. And for x is equal to L, when you put it in equation 2, you will get moment will be equal to 0. So you can put and you can check. Now we have 3. At x is equal to 0, we have moment is equal to 0. So this point at x is equal to L by 2, we have a moment which is, let this point is WL square over 8. And at x is equal to L, we have moment 0. You can see that shear force is a 1 degree line and the slope is decreasing. So bending moment will be second degree curve and that will be clockwise. So I will draw it by using a curve there. And similarly here we have the same scenario. The shear force is a decreasing, first degree and decreasing. So bending moment will be a curve and it will be like this one. So this was all about example 6-1, in which we have learned how to draw the shear force and bending moment diagram and how to write the equations, that is for shear force and bending moment, and by then using this equation we have drawn the shear force and bending moment diagram. I hope you are enjoying my videos and you are learning from it. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Example 6.12. So statement is the simply support beam in figure has the cross-sectional area shown. Determine the absolute maximum bending stress in the beam and draw the stress distribution over the cross-section at this location. So you can see this is a simply supported beam with a uniformly distributed load of 5 kilonewton per meter. The cross-section of the beam is shown over here. Clear, you can see all the dimension. The width is 250 millimeter. The total height is 300 plus 20 plus 20 is total height is 340 millimeter. The thickness of web is 20 millimeter while thickness of flange is 20 millimeter. So you have to determine the absolute maximum bending stress and then draw the shear distribution over the cross section at this location. So let's start with the solution. So our first step will be, if you remove the reaction supports, so definitely you will have a reaction force. Let this is RA and reaction force at this point is represented as RB. So we will find RA and RB. So how you will find that? So you will apply the equilibrium condition that sum of all moments about point B is equal to 0 and taking the counterclockwise movement as positive. So about point B, one moment is due to RA into perpendicular distance is 6, clear, and it will produce clockwise movement. So I will write minus 6 times RA, and the second moment is due to this distributed load. This when convert it into point load, so 5 into total length is 6, which will be 30, and it will be acting at the half of length of the beam, which is 6 by 2, and that is 3 meter, and it is producing counterclockwise movement, so it will be positive. So I will write plus, I will also convert this distributed load into point load, so 5 into total length 6 will be equal to 30 kilonewton, and that will be acting at a distance of 3 meter. So 5 into 6 into perpendicular distance is equal to 0. So 6 RA will become equal to 30 and 90. From here you will get RA will be equal to 15 kilonewton. Now you have RA, you can find RB by using another equilibrium condition that sum of all force along y direction must be equal to 0 and taking the upward force as positive. So 3 force, one is this one, other is this one, and third one is this one. Their sum must be equal to 0. So RA, which is 15 kilonewton minus 30 kilonewton plus RB is equal to 0. So from here you will get RB will also equal to 15 kilonewton. Now you have this RB, so you will then move toward drawing the shear force and bending moment diagram. Why? Because we know that maximum stress is equal to maximum bending moment into C divided by I. So we need maximum bending moment. That's why we will draw the shear force and bending moment diagram. So you have to draw vertical lines from the end of this beam, and first you will draw the shear force. Okay, so here we will have a shear force in kilonewton. So let each division is 5, so it will be 15, 15 will be here. So at initial point you have RA, so 15 point will be, first point will be here. Now you can see this is plus 15, and when you want to find the stress due to distributed load, this load, so this will be 5 into 6, 30, and that will be minus because it will be downward. So 15 minus 30 will bring it to minus 15 at the end. So minus 15 will be this point. So you have to join these 2 points by using a straight line. Definitely you will get shear. Now at the end you can see RB, which is plus 15 kilonewton. So this is minus 15, and this will bring it to the plus 15 will bring it to the 0 again. So At this location, this will be 3 meter, your shear force will be 0. Now we will draw the bending moment diagram. So again, for bending moment diagram, you will have to draw, this will be x in meter, where you have bending moment in kilonewton into meter. So now your first area is this one. Area under the shear force diagram will give you the bending moment. So this area will be equal to, since it is a triangle, so it will be 1/2 into its height, which is 15 multiplied by 3, and that will be equal to 22.5 kilonewton into meter. So at the distance of 3 meter, you have a bending moment of 22.5. So let each division is of, let's say 5. So this will be 20 kilonewton and 22 will be in between these two. So you will have a point like this. Let this is 22.5. Since this shear force line is a 1 degree line and slope is decreasing, so bending moment will be a 2nd degree curve and it will be clockwise. So we will draw the bending moment will be like this one. Okay, now you can see that we have this area which is also similar, and this area is, again, this is minus 22.5 when you calculate. So plus 22 minus 22.5 will bring it to 0 at this point. So you will have the bending moment curve will be like this one. So I will draw it. So this is your bending moment diagram. Now from this bending moment diagram, you can see your, I will write from bending moment diagram, you have maximum absolute bending moment will be equal to 22.5 kilonewton into meter. So you have this value. What about C? So we will go to C will be equal to, we will go to this section, and you can see this is its neutral axis. So C is the distance from neutral axis to the topmost. So this is C, which is 150 plus this distance, 150 plus this 20, which will be equal to 170. So C is equal to 170 millimeter, and we will convert it into meter. It will be 0.170 meter. Now we have this value as well, but we do not know I. So we will calculate I for this beam. So for that, I will copy this and we'll bring it to this position so that we can easily calculate I. So I, you can see that for I, we will find the moment of inertia of this upper flange and this web. So I will write the formula by using parallel axis theorem. So it will be equal to I bar plus AD square, sum of inertias of each element. So we have 3. One is this one, second is web, and third one is this one. So you can see the upper and lower plates or flanges are at equidistance from the neutral axis. So we will take only one, but we will multiply it with 2. So 2 multiplied by this plate. Let me clear this. So first thing is that you will take this plate. I have shaded it. So 1/12, its breadth is 250 millimeter, which in meter will be equal to 0.250 into h cube, and h for this plate is 20 millimeter. So it will be 0.02 whole cube plus AD square. Now what is the area of this plate? So its area will be 250 multiplied by 20. So 250 when converted into meter, it will be 0.250 into 0.02. This is the area multiplied by D square. Now D square is, if I zoom it, so D square will be from neutral axis till the mid of this. So this is your D. Clear? And this D is equal to 150 plus half of 20, which is 10. And that will be equal to 160 millimeter. So D will be 160 millimeter. So 160 millimeter is actually 0.160 meter, and it will be a square. Plus we have the middle portion. Now you can see the middle portion is this web one, and its moment of inertia will be equal to 1/12. This is 1/12, not 1/2. Okay, so 1/12 B, its breadth is, you can see, 20 millimeter. So 20 is 0.02, and its total height from this till this is 150 plus 150, which is 300, and that will be equal to 0.300 whole cube. We will not use here A plus D plus AD square, because you can see its D will be 0. From its, this flange web will have a midpoint over here, and this neutral axis is passing through centroid of this flange. So D will be equal to 0. So AD square term will be 0. So we will only left with this thing. So when you calculate all these values, so you will get I in term of meter will be 301.3 into 10 to the power minus 6 meter power 4. Now you have I as well, you have maximum bending moment, and you have C as well. So you can put it in this formula. So you will get the maximum bending stress. So we will write maximum bending stress is equal to maximum bending moment into C divided by I. So maximum bending moment was 22.5 kilonewton. So 22.5 into 10 to the power 3 will be converted into Newton. C was 0.170 divided by I is 301.3 into 10 to the power minus 6 meter power 4. So again, when you calculate it, you will get 12.7 megapascal. So bending stress maximum is equal to 12.17 megapascal. Okay, so this is the maximum bending stress. So if you want to find the stress at point B, let me clear it. So if you want to find the stress at B, so what we will do, you have this formula: stress at point B is equal to minus M into C is replaced with YB, distance from neutral axis to the point B, divided by I. So your maximum bending moment is 22.5 into 10 to the power minus 3. Now your B point is at a distance of 150 millimeters. So you will convert YB is 0.150 divided by I is 301.3 into 10 to the power minus 6. So again, when you solve it, it will be 11.2 megapascal. So this is stress at point B. So this was the extra which I have done because a student requested me to explain this problem. So that's why I'm going to explain it. Now we will do our next part, that is draw the shear distribution over the stress distribution over the cross section. So for that I have to draw the cross section. So let me draw it. So this is the, I will roughly draw it. So this is the beam. Clear? You have this beam. Okay. You have. Okay. So this is the beam, and this is your horizontal axis, and the axis that is outside is this one. Clear? Okay. So this is your neutral axis NA. Now, by using this formula, stress is equal to moment into C divided by I. Clear? So you can see that you will have maximum stress when C is from neutral axis to this point. This is your C. So when C is maximum, so you will have maximum stress. Clear? And you will have a maximum stress like this. So this will be your maximum stress. At point B, this was the point B, you will have a maximum stress like this. And at this point you will have zero stress. So it will be like, if I draw it like this one, and here you will have stress. So you will have maximum moment, maximum value over here, and then downward, and at center point you will have zero stress. So stress will decreasing. If I represent it over here, so this will be your stress at Y is equal to C at a C. So you will have stress like this, and again at this point you will have a lower magnitude stress. So your stress figure will be like this, and it will reduce to, at this point you will have a stress like this, and at this point you will have a zero. So if I represent it like this, so this stress at this point will be equal to 0, and stress distribution will be like this. Again, if I draw it, let me draw it over here. So if you have I beam like this, so you will be having a maximum stress over here, and then if this is your neutral axis, so this stress will be like this one. So if here top is decreasing, and this point it will be 0, and here it will be increasing. So this will be the stress distribution. I hope so. Also you can see that this is the force, stress distribution force, and it is producing a moment in this direction, because you can see this force is in this direction, and it is producing a couple, and this force is in this direction. So it is producing a counterclockwise movement, and this movement will be equal to 22.5 kilonewton into meter. So this was all about example 6.12. I hope you have enjoyed this video. Again, if you are new to my channel, then subscribe it and hit the bell icon so that you can get notification about my latest video. Thank you for watching and supporting me. And if you have any question, you can ask me in comment section. Take care. Welcome back. Problem 5.105. This problem is taken from chapter number 5, Analysis and Design of Beams for Bending, and the book name is Mechanics of Material by Beer Johnston, 6th edition. And the topic is Singularity function or Macaulay's method. So statement is, in part A, we have been asked, using singularity function, write the equation for shear and bending moment for the beam ABC under the loading shown. And in part B, use the equation obtained for M to determine the bending moment just to the right of point D. So you can see this is the beam having a point load at point C, and at this point we have P. Clear? Now, due to this loading, you have to find the shear force and bending moment equation using singularity function. So let's start with the solution. So when you solve this, and if you remove this fixed support at point B, you will be having a vertical reaction force By, you will be having a horizontal reaction force Bx, and you will be having a moment which is Mb. And what if you move this point P load to point A? So definitely you can move that by using force couple system, and you can see there is a perpendicular distance from point A till this, which is equal to P into L by 3, and it is producing clockwise movement. So I can write it, this movement will be equal to PL by 3. And similarly, if you move this point load to point D, so what you can do is that you can move it P, and there will be a perpendicular distance from P to D, which is L, and this is producing counterclockwise movement. So this PL over 3 will be counterclockwise. So again, I can write this as counterclockwise movement is like this. So you can see this will be also equal to PL divided by 3. Now we can draw a free body diagram for the beam shown below, or the one which I am drawing. So this is point B. You will be having a vertical reaction force By, you will be horizontal reaction force Bx, and you will be having a moment which will be Mb at point B. At point A, you can have this P load and a clockwise movement which will be PL divided by 3. And at point D, this is your point A, this is your point D. Again at point D, you have a vertical load P, and you will have a counterclockwise movement which is PL divided by 3. The distance from A to D can be obtained if you have L by 3 and L by 3, so it will be 2L by 3. So I can write it over here, this is equal to 2L divided by 3, and from D to B this distance is L by 3. Now by using singularity function, we will start from the left hand side, clear, and we will move toward right hand side, and the term toward right hand side, the last terms By, Bx and Mb, they will not contribute in this equation, so we will neglect them. Why? I have explained it in so many problems. You can also try at the end, they will give you the 0 value. So starting for the shear force equation using singularity function. So we know that singularity function is Vx. At this point, at point A, we have a load P. So due to this load, this P is acting downward. So this is the figures which is used for the low point load, since it is acting at point A. So the shear force equation is this one. But in this condition, A is equal to 0. So I will write Vx is equal to minus P into x minus 0 power 0. This is the shear force equation. Here A is equal to 0. Now at this point P, you can have this moment as well, which is PL over 3. So equation for the moment, for the figure used for moment is this one, and shear force, bending moment will be, shear force is 0. So it is not producing any shear force. So this term will be 0. Now the second load is point P, and it is acting at a distance of 2L by 3. 2L, this distance is 2L by 3, which is equal to A for this point load. So I can write minus P into x minus A. A is 2L over 3 power 0. And this moment is also having no shear force equation. So this will be equal to V of x will be equal to minus P, and x power 0 is 1. So it will be minus P, and minus P into x minus 2L by 3. That this is your equation number 1, which is the required shear force equation using singularity function. Now what I will do is that I will find bending moment equation using singularity function. And for that I can write it m of x starting for this load P. So bending moment equation will be this one. You can see bending moment for point load P is this one. So I will write minus P into x minus A for this P load is equal to 0. So I will write x square, not x square, x minus 0 power, this is 1. So correct it, this is 1. Okay, plus now this you have a clockwise movement which is equal to PL over 3. So for movement, the bending moment equation is this one, since this is for counterclockwise movement there, and here this is clockwise, so I will write it plus. So plus m naught is PL over 3, clear? So PL over 3 into x minus 0, because A is equal to 0 for this movement. So it will be having power 0. You can check it over here. The third load is this point P, and this is downward. So minus P into x minus A for this is 2L over 3. So minus 2L by 3 power 1. And the last term for this movement will be PL over 3, and this is counterclockwise, so it will be minus m naught. So minus m naught is PL over 3. Over here you can see moment is PL over 3 into x minus A is 2L by 3 power 0. Okay, so what we can do is that we can simplify it. Moment about x is equal to minus P into x plus PL over 3 because x power 0 is 1, and this term will be minus P into x minus 2L over 3 power 1 minus P into L over 3 into x minus 2L by 3 power 0. This is your equation number 2 and is the required bending moment equation using singularity function. Now in part B, we have been asked to use the equation obtained for M to determine the bending moment just to the right point of point D. So this is point D. So just write at point D means that at x is equal to 2L by 3. We will find this moment. So put x is equal to 2L by 3 in equation number 2. So moment about point D will become equal to minus P. X will be replaced with 2L over 3 plus PL divided by 3 minus P times 2L divided by 3 minus 2L divided by 3 power 1 minus PL divided by 3 into 2L divided by 3 minus 2L divided by 3 power 0. So we will get minus 2PL over 3 plus PL over 3 minus P times this term will be 0. Anything power 0 power 1 is 0. So minus P into L divided by 3 and this term will be 0. 0 power 0 is 1. So we can write it minus 2PL divided by 3 plus PL divided by 3. This will be 0. Minus P into 0 is 0. And minus PL divided by 3. Okay. So you can see these two can cancel with each other. So that will be equal to moment about point D. So moment about point D will be equal to minus 2PL divided by 3. Or you can say that this moment is equal to minus, if you want to remove minus, so it will be P2P L divided by 3 and that will be counterclockwise movement at point D. And this is the answer of this question. And that was all about this problem 5.105. I hope you have enjoyed this video and you are learning as well. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem example 1.6. This problem is taken from chapter number 1 stress and book name is Mechanics of Material by R.C. Hibbeler and 9th edition. The statement is the 80 kg lamp is supported by two rod AB and BC shown in figure. If AB has diameter of 10 mm and BC has a diameter of 8 mm, determine the average normal stress in each rod. So you can see this is the lamp clear and that is supported by rod BC and AC and the weight of the rod lamp is going to act downward. So due to this downward weight, there will be a tension in this AB and BC. As a result of Newton's third law, the rod will exert force on lamp in this direction. So I have shown this in free body diagram. The weight of the lamp is acting downward and the force this rod BC acting on lamp is FBC while the force of rod AB on lamp is FAB. FAB makes an angle of 60 degree with the horizontal while this FC, the ratio of the triangle is shown as 3, 4, 5. So you have to determine the average normal stress in each rod. So let's start with the solution. The first step is that this weight is acting downward and weight is equal to mass into G. So mass is given as 80 kg and G is 9.81. So when you solve this weight acting downward will be equal to 784.8 Newton. Now we will apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So you can see that this FAB will have two components, one along x which will be equal to FAB x component and one along y which will be equal to FAB y. Similarly, this FBC will have two components which will be FBC x and one along y which will be equal to FBC y. So from here this minus FAB x component plus FBC x will be equal to 0. So you can see that this angle is 60 degrees, so it's one component. That this is FAB, so this component will be equal to FAB cos of 60 degree and this vertical component will be equal to FAB sine of 60 degree. Why? How? Because if you take cos 60 degree, so cos 60 degree will be equal to this FBX divided by FAB. So FABX will be equal to FAB cos of 60 degree. Similarly, this FAB y component will be equal to FAB y. And same is the case if you take this component, which is that this force will be FBC. So this FBC x component will be this one and FBC y component will be this one. So for example, if this is theta angle, so if you take cos of theta, so cos of theta is equal to 4 divided by 5 and this FBC x component will be equal to FBC into cos of theta. So FBC into 4 divided by 5. This will be FBC x and this FBC y component will be equal to FBC sine of theta. So you can put the value of sine of theta. So sine of theta is perpendicular over hypotenuse, which is 3 over 5. So FBC y will be equal to FBC into 3 divided by 5. Now you can just plug it in this. So FAB is this one. So I can write minus FAB into cos of 60 degree plus FBC x. So this is plus FBC into 4 over 5 is equal to 0. Let this become your equation number. This is your, let me name this equation number 1. Now we'll apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So one upward force is this one, which is equal to FAB sine of 60 degree. Another one is this FBCY, which is this one, plus FBC into 3 over 5. Clear? And the downward force is weight, which is minus 784.8 Newton. Their sum must be equal to 0. So I can rewrite it this FAB into sine of 60 degree plus FBC into 3 over 5 minus 784.8 is equal to 0. So it means that your this FAB into sine of 60 degree will be equal to 784.8 minus FBC into 3 over 5. And this FAB will be equal to 784.8 minus 3 by 5 times FBC divided by sine of 60 degree. Clear? So this is your equation number 2. Now put equation 2 in equation number 1. So this is your equation number 1. So FAB will be replaced with this. So minus 784.8 minus 3 over 5 times FBC divided by sine of 60 degree into cos of 60 degree plus FBC into 4 over 5 is equal to 0. Now you will get this equation. So if you solve this equation, so you will get FBC will be equal to 395.2 Newton. Now put the value of this. Put FBC is equal to 395.2 Newton in equation number 2. So you will get FAB is equal to 784.8 minus 3 by 5 multiplied by 395.2 divided by sine of 60 degree. So you will get this FAB will be equal to 632.4 Newton. Now you have forces in both the rods. So we will go towards the average normal stress in each rod. Since rod AB and BC both are in tension, so we will find for rod AB, average normal stress in rod AB will be equal to force in rod AB divided by area of AB. So force in rod AB is 632.4 Newton and diameter of rod AB is given as 0.01 meter. So pi by 4 d square. Let me write pi by 4 d. Diameter is 0.01, not 0.001, 0.01 square. So when you solve this, you will get the average normal stress in rod AB comes out to be 8.05 megapascal. Now for rod BC, we have average normal stress in rod BC will be equal to force in BC divided by area of BC. So force in BC is 395.2 Newtons. Clear? And area is pi by 4. What is the diameter? So diameter is given as 0.008. So pi by 4, 0.008 square. So when you solve this, you will get average normal stress in rod BC is 7.86 megapascal. So that was all about this average normal stress in rod AB and BC. Now what if I represent this average normal stress in rod AB? So let this was the rod. Clear? For example, this is the rod having this diameter. Clear? So this is the load FAB. This is FAB, which is equal to 632.4 Newton. And if you want to represent this element, clear, stress on this, so the stress will be like, for example, this is the same rod AB, so stress on this rod will be like this. And if you represent them on element of cubic element, so this stress will be tensile. It will be like this. That is 8.05 megapascal. Same is the case. You can draw the stress and force diagram for rod BC. So that is all about this problem, example 1.6. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem example 1.8 that is taken from chapter number 1 stress, and the book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is member AC shown in figure 1-18A is subjected to vertical force of 3 kilonewton. Determine the position X of this force so that average compressive stress at smooth support C is equal to average tensile stress in the tie rod AB. The rod has a cross-sectional area of 400 square millimeter and contact area at C is 650 square millimeter. So this is member AC, clear, that is subjected to a point load of 3 kilonewton. There is a tie rod AB which is in tension and this point C which is in compression. So you have to determine this X for which the average normal stress in tie rod due to tension will be equal to average normal stress due to compression at C. So let's start with the solution. So first step is that we will remove this tie rod and the reaction force by the C, and we will draw the free body diagram I have shown over here. You can see that it is given that tie rod AB is in tension. Clear. As a result, this tie rod will exert a vertical force upward on this member AC. So I have represented this as FAB, and point C is in compression. So as a result, this support will apply a vertical force FC on this member, which is already shown here. So here three values are unknown: FAB, FC, and X. So we'll find them by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see FAB, which is upward, so it is positive. Clear. 3 kilonewton force is downward, so minus 3 kilonewton. So in Newton it is 3000 Newton, and plus FC, which is also upward. So their sum must be equal to 0. So I will write FAB plus FC minus 3000 Newton is equal to 0. This is your equation number 1. Now we'll apply another equation of equilibrium, that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, first moment is due to this 3000 Newton force and perpendicular distance is X. It is producing clockwise moment, so it will be negative. So I can write minus 3000 multiplied by X. The second moment is due to this load, which is FC, and perpendicular distance is this 200 millimeter, and it is producing counterclockwise movement, so it will be positive. So I can write plus FC into 200 millimeter is equal to 0, and this is your equation number 2. Now in equation number 1, FAB and FC are unknown, so we cannot find this, and in equation 2, FC and X are unknown, so we will find this unknown by using a third equation. So let me write it. The statement was given for average normal stress. So let me also tell you, it is given that the average compressive stress at smooth support C, average compressive stress at C is equal to the average tensile stress in tie rod. So average tensile stress in tie rod. Clear? So what is average normal stress at C? So it will be equal to, definitely it will be equal to force at C divided by area at C, and average normal stress in tie rod is equal to FAB divided by area of AB. So put the values in this equation. So we do not have FC, so FC divided by its area at contact C is equal to 650 square millimeter. So I can write 650 square millimeter is equal to FAB, which is also not known. So FAB divided by area, cross sectional area of AB is 400 square millimeter. So 400 square millimeter. So from this, what we will get, this FC will be equal to 650 divided by 400 multiplied by FAB. And when you solve this, you will get this FC will be equal to 1.625 times FAB. This is your equation number 3. This is your equation number 3. Now put value of FC in equation number 1. So when you put it, FAB plus FC will be replaced by 1.625. FAB minus 3000 will be equal to 0. So 2.625 FAB will be equal to 3000 Newton. So FAB will be equal to 3000 divided by 2.625. So when you solve this, you will get FAB will be equal to 11143 Newton. Now what we will do is that put value of FAB in equation number 1. What is the equation number 1? So equation number 1 is this one. So you will get 1143 plus FC minus 3000 will be equal to 0. So from here you will get FC will be equal to 1857 Newton. Now you have this FC, clear? So what we will do is that you can just put the value of this FC in equation number 2. So I will write it, put the value of FC in equation number 2, and equation number 2 is minus 3000 into x plus FC into 2 plus FC, which is 1857 multiplied by 200 is equal to 0. So minus 3000 x plus 1857 into 200 is equal to 0. So it means that 3000 x is equal to 1857 multiplied by 200, and x will be equal to 1857 multiplied by 200 divided by 3000. So when you solve this, you will get x will be equal to 124 millimeter. So this is the value of x is equal to 124 millimeter when a load of 3 kilonewton act at a distance of 124 millimeter from point A, and it will result that average normal stress, tensile stress in tie rod AB will be equal to the average normal compressive stress at the smooth contact surface at point C. And that was all about this problem, example 1.8. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.